We are continuing in 1.5. Let's look at the next theorem. Cancellation of inverse matrices. So now we can answer the question we had a bit ago. This one says, if the matrix C is invertible, then 1, if AC equals BC, then A equals B. Again, C has to be invertible, right? And then 2, if CA equals CB, then A equals B. So it's just either side. Proof is pretty straightforward, right? You just got to multiply C on the correct side, or C inverse. So let's look at the proof. But pay attention to formatting with things you have to say. So assume what? Assume the hypothesis, right? C is invertible. Assume C is invertible. And so now we're going to look at like that. Well, let's do this in steps. We'll do this. So assume C is invertible. Okay. Then we know C inverse exists. And now suppose, so basically we'll do both of them. Why not? So try to do it. I mean, this is a very reasonable one to do. Now we're going to assume this is true. And then you do right side multiplication of C inverse, and then it has to work out. So let's suppose AC equals BC for matrices A and B, leaving off a few little details here and there, I guess. So then I get AC equals BC, and then we do right side multiplication of C inverse, associate appropriately, like that. And that's equivalent, so let's just do equivalencies here. So the first one is equivalent, or if and only if this is true, if and only if A times I is equal to B times I, if and only if A equals B. And so the other side is the same way, right? Hardly have to show that, but I kind of feel like we should. Let's move these up so I have space. Okay, so again, why don't you try it? 2, suppose now CA equals CB. So if we start off with CA equals CB, if and only if C inverse CA equals C inverse CB, then you have to associate appropriately. That is just I. So it's I times A equal to I times B, if and only if A equals B. Okay, so that's pretty straightforward once you have invertibility. If it's not invertible, of course, that can't work. So it only works because C is invertible. All right, next theorem. This is uniqueness of a solution for the matrix equation. So this one says if A is invertible, then AX equals B has a unique solution. Or we could say it has a solution and it is unique. So only one. So it exists and it's only one when we say that. So first we'll show it has a solution and then we will show it is unique. So here's a proof. It's a two-step proof. First we will do our assumption. Assume A is invertible. Okay, then A inverse exists, and we have AX equal to B. Multiply both sides by A inverse, left side multiplication. Okay, like that, and then we're going to associate appropriately. Could be like two steps there, but it's not going to matter much there. So that's I times X equal to A inverse B, and then you've shown that that's a column vector. So I times the matrix is just, or vector is just X, which is equal to A inverse B. So that must be a solution because A inverse is invertible, so we can do that. Otherwise, you can't do that. Now, for uniqueness, let's show you how would you do that. So same process as before for uniqueness. To show something is unique, we assume there's two solutions and then we show that they're equal. So let's suppose both x1 and x2 are solutions, are two solutions to AX equal to B. So we're supposing we have two different cases. Then we will show that they are equal. So what you do is we basically are saying then that we have A x1 is equal to B, which is equal to A x2. They're both, in other words, they're both equal to B. So if those are both equal to B, then this is like a transitive property, right? If this equals this and this equals this, then that equals that. Okay, so this is a transitive of equality. We can then say AX1 is equal to AX2. Okay, now we apply what we just did above, the cancellation property. So apply the cancellation property above. And I mean, you basically are just multiplying both sides by A inverse. I mean, that's true, but that's essentially what you're doing then. So left side multiplication gives us this. And so that is I x1 equal to I x2. Let's put in some parentheses. And so we get x1 is equal to x2. Therefore, the solution is unique. So since they're equal, we're done. Like, that's it. We know they're unique. So therefore, the solution is unique. you don't have to always make these types of conclusions because you've already demonstrated what you were trying to do when you get to here. Okay, so that's all has to do with invertible matrices is in it. So we're kind of going back and forth between concepts of just matrix and concepts of the system, right? They're related, but we are there's a whole other field of study of just matrices, not solving systems. It's kind of how it got created in the first place, but or discovered, however you want to think of it. Okay, next big thing, and I think it's the last thing in this section, is finding matrices or calculating matrices. So we will go through that. Kind of like row reduction, Gauss-Jordan elimination. It's exactly like that, actually. We need to know how to do it all the way through, show how you got it. Give it enough time, you'll do it perfectly. But you don't have to be like crazy proficient at it. Okay, so let's do a test case right here. So first we'll just do some product and see what happens. So write down, now we want to calculate matrices. Determining, if they exist. So calculating, oops, I spelled that wrong. So calculating inverses. So first we'll just do a simple example, see how it works out. Okay, so given, let's just suppose this is kind of like homework simple stuff at first here. Given A is equal to 1, -3, 2, -5, and B equal to -5, 3, -2, 1. Like that. Then how would we show those are inverses? What do we know about them? So what would you do? So show how about let's say instead of showing, determine if A and B are inverses. So to do that, you would do their product, right? So you basically do A times B, work it out, see if you get I, and then you do B times A, work it out, and see if you get I. So you got to do technically both sides. And then if you get this, then you conclude that they are inverses. You can say A is B inverse, or B is A inverse, or either way. So let's do that product and check it. Okay, so I'll give you some space here. So you do A, so 1, -2, -3, 2, -5 is A, times B, -5, 3, -2, 1. You do that product and see what you get, and I believe you get I. Same thing over here, -5, 3, -2, 1 times A, 1, -3, 2, -5. So this is how you can check it, or it's just verifying the concept. So do that. You can do that by hand. You can do that on a calculator and check it. I'll do it quickly here on a calculator just to show one of them. So the first one, you put in a matrix. Okay, so you have 1, 1, 3, and then 2, 5. And best way to do it is to store it as a matrix, as like a variable. So you type it in and then you hit a variable and store it. I'm not going to do it this time, but next matrix is B. So it's 5, negative, 3, and then 2, negative, and then 1. And you do the product, and sure enough, you get the identity matrix. Then check the other side, and you should get the same thing. So 1, 0, 0, 1. 1, 0, 0, 1. Okay. So therefore, A and B are inverses. Or you just say A equals B inverse or B equals A inverse. Either way. Doesn't matter, of course. Okay, so just a little exercise to check if they're inverses. That's the whole idea there. Now let's go through the process of finding inverses. So this example is given a matrix, find the inverse. So find A inverse if it exists for the matrix A equal to 1, negative 1, 2, 0, 2, negative 1, 3, negative 1, 4. Okay, so this is how you do it. What you do first is you form this matrix. You do A, and then you augment with the identity matrix of the same size. Okay, and then 2, you row reduce. So you reduce using the row reduction techniques to, so actually, I have more description than I thought. So row reduce, so form that matrix. Let's just do it to the side here. What the heck? So let's form the matrix. So it's 1, negative 1, 2, 0, 2, negative 1, 3, negative 1, 4. And then you augment with the identity matrix like this. Okay, and then you perform the row reduction just like you would. So you do row reduction and see if you can get this form. So you end up with the identity matrix on the left side. It's like you flip them. And so this would be, and then we usually say this is like B or something. And then if you do indeed get the identity matrix here, then B is the inverse. If you cannot form that, then it's not invertible. Okay, and there's other ways to tell. Now, you can always just check this on your calculator right now. That's fine. I don't care if you verify stuff, but you got to be able to show all the operation on it. So let me write out what you do. So 1 is that, you form that. Then 2, you reduce this form until it has the form, and I'll call it UB, because we don't know if you can find it to be I, but that's your goal, where U is reduced row echelon form. Reduced row echelon form for the matrix A. if A is non-singular, meaning it has an inverse, just using some notation, some vocab that I want you to know. So if A is non-singular, then then U will equal the identity matrix, just like I mentioned. And B, in that case, equals A inverse. So identity matrix, that is the inverse right here. So that's the process. It's, just like row reduction is quite tedious to do and work all the way through. So I will go through it once, and then we will practice it, have you practice it. So let's do that. So let's take this matrix, and we'll use a lot of screen here. So we're going to take this matrix and put it to the side so I can show you my steps. And we will go down the list there. Okay, so let's try it. So I have it worked out. So, I'm going to follow one method of doing this so we can stay together. So recopy row 1, and then we will put zeros first in this lower triangular, and then we will put zeros in the upper, just like we did before. That's your process. And then last, we'll divide out, if we need to, by your diagonal. So there's already a 0 there. So this row we can leave, and then we want to get a 0 here. So probably what? -3 row 1 plus row 3? Yeah, I think that's going to work. So recopy row 1. And then you have to go all the way through and do the same thing with the right side. Recopy row 2. And so let's tell me what you're going to do. You're going to do -3 row 1 plus row 3, and then we're going to put it right there in row 3. So you should get 0, 2, -2, and then see, now you got to keep going over here, and you get -3, 0, 1. Okay, now keep going. Let's do this again. And like I said, I'm going to use a lot of screen paper here. Recopy row 1. So 1, -1, 2, 1, 0, 0, 0, 2, -1, 0, 1, 0. And let's now go ahead and get this to be 0 right here. So you just subtract those two. And like I mentioned, or maybe you heard me mention it, but I like to do the product and then add, just because subtraction always can be kind of weird. So -3 row 3 plus row 2, and let's put it back here. And that'll zero out my lower triangular. So I get 0, 0, 1. But I need to keep going. What does the right side look like? Well, that looks like 3, 1, -1. So now I have the lower's done. So you got to be careful not to mess that up when you keep going. Now let's work on the upper. So when you work on the upper, we do these first, and then we do the -1. Then we come back and do this. Okay, so let's continue. So we have, and I do this 2 steps at once. So, so row 3 is done. So don't change row 3. It's exactly what we want. 0, 0, 1, 3, 1, -1. That's too squished for me. Let's move that out a little bit. Okay, that's better. So we will do next. We are working on those. So let's just do negative 2 row 2 plus row 1. So negative 2 row 2 plus row 1. Put it there. And at the same time, we can just add row 2 and row 3. And put it in row 2 right there. So by doing so, verify this. Maybe pause and check it out. You get 1, 3, 0, 1, 2, 0. And then the next one, you get 0, 2, 0, 3, 2, negative 1. Because you're going all the way across as well, right? Okay. And now we got to get the last one to be a 0. So this here, and you can only work with row 1 and row 2, because otherwise, like this will zero it out. So don't go here. You can only work with these two. So that's got to be what, a negative 2 and a negative 3 and a 2, or 2 and negative 3, right? That's the only way you can do it. So this last one, let's recopy row 3 because it is done. Recopy row 2, it's what we want. We can divide out that 2 really easily. Don't worry about that. Never worry about the diagonal. Okay, then the top one, negative 2 row 1 plus 3 row 3. I mean 2, sorry. I just said not to use that row. Negative 2 row 1 plus 3 row 2, and place it in row 1. So we get a negative 2, 0, 0, 7, 2, and negative 3. Okay. Almost done, right? All we got to do is what? All we have to do now is divide out by our diagonal. If they're not 1, then you just divide them out. So let's go ahead and state that. As I mentioned, row 3 is done. So just recopy it. And then we'll do negative 1/2 row 1, and then 1/2 row 2. So I get 1, 0, 0, negative 7/2, negative 1, and 3/2. Then I get 0, 1, 0, 3/2, 1, and negative 1/2. And just remember, I have this written down. I'm not going through every little detail in my head as I go through this. It would take you a lot longer to figure this out, most of us at least. I usually go a lot slower. I'm doing all my arithmetic there. So just keep that in mind. This takes a while, and I have you do this once. And you got to show your work. You have to tell me what you're doing. You can just plug this into a calculator computer and bam, that's worth nothing. Okay, so I want you to be able to calculate this because we'll be doing operations that are important to see the structure of the matrix when you do more of the theory concepts. So you got to be able to do it. So our matrix, this is the identity matrix, right? So we have that form of the identity matrix and B. So since this is the identity matrix, B is A inverse. So therefore, B equals A inverse. And then you can check that. All right, so check it by doing the product. And frankly, I wouldn't even bother doing it by hand because you can mess that up too. So check it on a calculator if you get the identity matrix. Now, when you divide by 2, you should have exact numbers because it'll just be a 0.5 sort of situation. But if those are repeating decimals and you do this on a calculator, it can be kind of messy. just got to be careful with that. So check it, what is what you have, but basically we check this. Let me finish my statement. A inverse, and then see if that's A inverse, and see if you get the identity matrix. So I want you to verify stuff with your calculators, but make sure you can do this by hand all the way through. So let me write down just because. So we have, so therefore A inverse is that matrix. So it's the matrix -7/2. Whoops. It's like when I look over to see what I'm writing next, I just pause and then it does that. -7/2, -1, 3/2, 3/2, 1, -1/2, and then 3, 1, -1. So check that out. See if you get the identity matrix when you multiply by A. A is back here, way back here. Okay, so there's my A, way back here. These do take a long time to work through. Okay, so that product, so that's what you would have and use if you were solving a system. So basically, I mean, here's the thing. If you put any B on the side here, it has more to do with the coefficients, not B. So whatever B is, you're going to find a solution. You multiply by A inverse and B, and then that's your solution. Okay. That wraps up, I think, 1.5. Yeah, we finished 1.5. We still have 1.6 to do, which is actually a really important section. Takes us into what's called homogeneous systems, subspaces, and bases. So that'll take probably 3 videos or more to get through all of 1.6. All right, so stay tuned.